Good. Thanks everybody for coming. So good afternoon and welcome to the 8th Monte and Ahuja Distinguished Lecture. I'm Professor Richard Vasquez. It's my pleasure to welcome you all here today. This distinguished lecture series is supported by Monte and Ahuja, honored and highly accomplished graduates of Ohio State. They consider their charitable and philanthropic support of the university as an investment in the next generation of trailblazers in science, technology, engineering, and mathematics. The series aims to attract highly accomplished and illustrious individuals, as well as those on their way to national and international renown. In addition to showcasing the work of current experts in engineering and science, we hope to inspire our students to achieve excellence and eminence in their own future careers in government, industry, and academia. Today it is our pleasure to have with us distinguished Professor Anil Prinja from the University of New Mexico, Department of Nuclear Engineering. He will be presenting on the topic of modeling stochastic neutron populations with branchy Markov process theory. As usual, at the conclusion of the lecture, there will be a presentation of an honorary plaque to Professor Prinja, and after that, please plan to join us upstairs for a reception in room E100. I would now like to welcome our distinguished speaker, Professor Prinja.
Thank you, Dr. Vasquez. It's a real honor for me to be here presenting in this very distinguished lecture series. When he told me first he invited me to come to the seminar, I had no idea this is what he had in mind. I almost came in a t-shirt and shorts because he said it was going to be very warm as well. Luckily, I back to time. Great pleasure to be here. It's also my first trip to OSU, and I'm surprised how large a city this is. And so far, I've been certainly very impressed with the engineering faculty and some of the students that I've already met. Good story here. There's a real buzz, and there's been a recent chair back home, and I know how important that is for chairs to feel a sense of excitement and not just complaining. That's only when you leave it every year. So let's see, about 15 minutes.
Yeah.
I've got about 2 hours worth of material here, but I promise I won't go through everything. So so I'm not an experimentalist, and I'm not a big simulation type either. I'm sort of old school. So I was taught by people from who were out there busy developing new fields, breaking new paths in the 50s and 60s. So I'm primarily a theoretician at heart, but I'd like to say that my research interests are at the intersection of physics, math, applied math, and some numerics. So a typical thesis topic for my student is one where we get into we formulate a problem with some we use some physical principles, we formulate it mathematically, we study some properties mathematically, and then we put it on the computer to do some simple testing, some different testing. A lot of my students, and last count since I'm about to retire now in a couple of years myself, I can say I've graduated about 30 PhD students, and more than half of them are at Los Alamos, and half of the rest are at Sandia, and I don't know what US some of the others are. One of them is in Indonesia. I have the area we work in, radiation transport. That's our main customer. The other national labs, more so than even the nuclear power industry, and I don't know, but I think that. And so that's what funded most of my research there was Los Alamos National Lab, the Boltzmann Lab, and San Diego. And yes, you can say, well, they require a lot of heavy-duty computation types, and there's no doubt that if you know your programming languages, your computer architectures, you know a GPU from a CPU, and all of that. They really want you. But a lot of that stuff you can pick up there. What you can't pick up is the theoretical background, which trains you to be a problem solver, a thinker, where when you encounter a new problem, you will have the confidence to then to actually formulate a transport. So that may be very self-serving because that's where I feel like that's what I have to offer. But it's worked. My evidence, the evidence is the fact that I have my students are there. They sound fun to me. They're happy. You have to work on problems that they're interested in, but they are interested. These labs have some fascinating problems, real challenging problems. Frankly, I don't think there's much of a challenge in the nuclear power industry in terms of the fundamentals. They're fairly established in their way they're going to do things, and they haven't much. There's some interesting new innovations, as we were discussing earlier, that are happening in the industry, but it's not going to be in methods. Although, from some of the stuff you're working on, certain subjective designs can be something different. So, with that said, I'm going to talk today about something that's been my passion. It's stochastic processes as applied to neutron distributions in different assemblies, different various assemblies. And none of this will apply to nuclear reactors because if you have to address problems like this in nuclear reactors, you're in trouble. Because you want reactors to be predictable, right? You want to build a reactor, you need it to run, and you don't want to have to worry about statistical deviations. So it's a heavy dose of theory and math, but there will be results. I'll try and set this up in a way where it's fairly pedagogical initially, and then I'll just jump into it without a lot of detail. And so hopefully everyone will take something away, and as the talk progresses, it's going to be more and more targeted towards the transport group over here, and then maybe that will end. So so I've had a few current students working on this. Patrick O'Rourke is, Lano will just not wait to get their hands on him. They've got a lot of work lined up for him. Jawad is my current student. So Patrick works on Lano applications, and you know what those are. Jawad works on the other extreme, which is nuclear non-proliferation applications of some of this stuff, right? We're looking for signatures. And so I want to give you an exposure to all these problems, that domain. I have a joint appointment with Imperial. That's sister college to the one that I graduated from many years ago, and I go back there. I actually had a student there, and she's at AWE, which is the Lano, UK's Lano. It used to be called Atomic Weapons Establishment, now it's just AWE, just like AFC, right? One collaborator is there, Dave, actually there's a couple more in this new project that we'll know about. And so, with that, again, thank you so much for inviting me, and I hope you'll feel that it was worth it. So, let me get started. So, by way of background, right, we're looking at, by the way, this is a very huge screen, and it's something like I have to be over there, so it's the first time I'm seeing this, and so I hope the quality works out. But we have we talk about paradigms, and so over the last 50 years or whatever, since the advent of computing, one paradigm that's evolved in computation science and engineering is to model systems that is composed of particulate systems, right? And so typically, whether you're in a solid or liquid or gas or a plasma, you represent your system as being a collection of point particles. They're structureless, so we don't ask about the size of the particle, we don't ask about the properties, and they're generally classical. As I say over here, quantum and relativistic effects are added after the fact in some way through interaction parameters, what we engineers call cross sections, right? And these particles, literally wherever they are, whatever structure they're in, they interact with each other, and the forces are either long range, what I call electromagnetic or Coulomb forces, or whether they're very short range, which are nuclear forces like neutrons interacting with nuclei, or these are ions interact with electrons, vice versa, as well as atoms interacting with atoms, right? So with that knowledge, you can proceed in two different ways to then model reality. So the obvious way is to write down Newton's equations of motion for each one. These are classical particles, so I'm not talking quantum mechanics, I'm not talking about Schrodinger's equation and uncertainty, but that's done as well at a more fundamental level. when you're looking at just the properties inside of simpler atomic systems, molecular systems, you can get into some level of detail. But we want to be able to model on a large scale. And so so you can write down the Newton's equations of motion. Those for a system consisting of k particles. You can track the position of every individual and the velocity, and as they interact with each other. This is the total force on the kth particle from all the other particles around there. Okay? And so k has to be some number. And if I were to ask you what's a number that comes to mind when you look at these applications, you would say a Pelvic number, which is pretty huge. 10 to the 23 last time I checked. Okay? And so when we do simulate, for example, molecular dynamics is a very big field now. The numbers you typically simulate, and the numbers get large. Used to be tens of atoms now. Then it became thousands and millions, and now maybe you can get up to, I don't know, technically 8 some particles with the present computer architectures that we have. But in any one of these, a very small amount of any of this material has a lot more than just 10 to the 10 particles. So you're again just doing very representative things. So this sort of approach is still limited. That's right.
It's just okay. So let me know if I'm now shouting if I'm too loud. And so to study more macroscopic gross behavior, you have to shift to a statistical approach. And that, of course, is where you now shift over, instead of asking for the position and velocity of every particle, which is too much, which is more information than you need, you want to shift over to some sort of averaged behavior. And for that, we introduce this idea of a distribution function or a phase space density, where you ask for the average number of particles in a volume element, a configuration, as well as velocity volume element at some time t. And from this, you can extract all the information that you'd want, the macroscopic information that you need. Okay, so how do we write? These are very simple equations. What is the equation for that? Well, that back in the late 1800s, mid to late 1800s, the people like Maxwell and others were beginning to develop the atomistic theory of matter, and Boltzmann came along and established the foundations for what's called the kinetic theory of gases. And there he was with these assumptions, where we're basically dealing with a dilute enough gas that when there's a collision between two atoms, that there isn't a third atom interfering, which obviously means you've got trouble with liquids and solids and the like. But if you're an otherwise rare dilute gas, you can get that they have elastic collisions between them, so that there is conservation of energy and momentum. In those collisions, the particles don't get excited. So there's no change in the internal state, that these collisions are following on from the basic physics, basic interactions here, that they have to present, individual collisions have to be micro-reversible, which means that if these are the two particles coming in and having a collision, and these are the outgoing velocities, if I reverse those velocities, then I recover the outgoing velocities. Okay, so that's reversibility. As it happens, Boltzmann's equation, which he then, this was then the equation that was developed for the distribution function. It's a continuity, it's a balance equation that looks at a balance in that phase space volume element. The distribution changes in time due to particles just leaving. This is what we call streaming. They change, streaming in configuration space, then they change due to change in velocity, due to forces, external forces, and then they change due to collisions. The velocities change due to collisions, right? So that's our generalized volume element, which we call the phase space. As this complicated collision operator, this is the rate at which these collisions occur depend on the distributions of the particles there, of the two particles coming in to the collision and leaving the collision. Okay. And from this distribution function, you can get your macroscopic properties: the density of the gas, the average velocity, and the energy, and all of that. Okay. So this approach. So we go from a fairly simple two-variable, literally the velocity and these are vectors, velocities and positions over time, but a lot of them we go over to a a field description now, but these are where now you've got a single equation, but it's 7-dimensional. Right? You've got 3 spatial dimensions, 3 velocity dimensions, and time. So this is a completely different approach than to it, but it's still more practical in terms of getting at the quantities we want. And we're not always just interested in these macroscopic parameters. We often want to, and especially in nuclear reactors or nuclear applications, we really do need to know what the distribution function is. So this equation occupies a pretty, and for the last, well, let's see, he published his equation in 1905, something like that, and then he killed himself in 1907. Impression. Before you could get really get, but look at that. Since then, this equation has formed the basis, or we refer to it as a paradigm in that. So there are 3 different things. You saw over here that you have products of the unknown there, right? So it's a nonlinear problem. The operator is nonlinear. If you go into plasmas, then the force depends on that too. The self-consistent electric magnetic force. Things can get very out of hand. And so if you have the nonlinear Boltzmann equation, what are some of the nice things about it? Well, if you do what's called the Hilbert asymptotic expansion on it, which is a weak collisional regime, you get hydrodynamics, the equations of hydrodynamics out, which is basically, right? If you do what's called, if you're collision dominated, then you can do what's called the Chapman and Enskog asymptotics, and that gives you the Navier-Stokes equations, the equations of fluid dynamics. So there you're now getting fluxes as well, and so on. And then we know from independently that the equilibrium distribution has to be this Maxwell-Boltzmann velocity distribution, which you can prove under very general conditions that the nonlinear Boltzmann equation delivers that. Okay. However, it's nonlinear, and it's solved largely through Monte Carlo methods. But there are simplifications that arise. For example, if you're in a dilute gas, this didn't count very well, right? Then you can perturb the distribution about a local Maxwell-Boltzmann distribution. And so now you're looking at perturbations, and you end up getting what's called the linearized Boltzmann equation. It's linearized about the local equilibrium distribution. And so, and that's applied in rarefied gases, upper atmosphere, things like that when you're looking at. And finally, when you can assume that the species of interest is dilute enough and it's in a background that's much more dense and does not change, right? As it would be, for example, any radiation, in this case neutrons, that are moving around in a solid medium. Then you have something called the linear Boltzmann equation, where one of those distribution functions that you're colliding with is assumed to be completely known, and the neutron energy is high enough that you can consider the nucleus it's colliding with as stationary. Okay, so this is what nuclear engineers work with. It's called the linear Boltzmann equation. So we are interested in the distribution of neutrons in what's called some kind of a nuclear assembly, whether it's a reactor, whether it's a research with some small sample, or whether it's a weapon. You are interested in that distribution function. And so that's what it's a little simpler. And so here are some typical things. You've got a beam coming, you've got neutrons coming in. We could be in some heterogeneous system. Neutron paths follow different depending on those interactions that are to be defined. Okay, so that's my nod to mechanical engineering and aerospace engineering, because you guys do kinetic theory, I hope. So I hope some of this resonated a little for you guys. But I love this. If you start thinking about it, you really do realize the Boltzmann equation is ubiquitous. It is everywhere. The Boltzmann equation can be written down for anything that has a large population. Okay? So certainly reactors, in homeland security, so this is where we look at neutrons and photons are important. Materials, constantly, right? And you have electrons and ions, and that's the symbol for heavy ions, X-rays, lithography, implantation, radiation damage, medical treatment, right? Therapy, electron therapy, hadron therapy, space, protons, alphas, ions coming in from cosmic rays, for example. All of these can be described by some kind of a Boltzmann equation interacting with some background. And the bit of graphics, you're working on, we all know that, right? And then, but a lot of other fun stuff. Space debris, you wouldn't think about it, but you can represent it as a particle that interacts with other particles, and if there's a collision, it breaks up into smaller particles. That's a bit like aerosols too, right? or they can, where aerosols can coagulate and make into bigger. So they're all Boltzmann type equations. Each one of them looks the same, as I showed earlier. The form is the same. It's that one term in there that distinguishes, that's this term. The whole character of the problem changes by defining this object W, which is the physics. All the physics in the problem, all the interaction frequencies, the type of interactions are all contained in there. With that one change, this equation can give you completely different solutions. So this is an interesting archaeology. Some time ago. So muons are all around us. They come from their cosmic ray products, right? So they're all around us. So it's like a massive source of radiation. So for imaging, they're ideal. But they penetrate. They're very penetrating. They go through, right? So they have very, very long mean-free paths. So they image the interior of the pyramids, and actually discovered certain rooms inside there that they hadn't seen before because from there. Now they're also using muons for other kinds of tomography, for looking at for special nuclear materials, that's being sneaked across borders. And if you have a big truck and you're hiding a little bit of plutonium in there, how are you going to detect it? Well, but you have to be patient. The fluence is not that high, the flux isn't that high, and so you can image and you can find heavy objects. They found that by looking at using proton beams to irradiate classical works of art, you'll find other paintings behind paintings, and so you discover that, and that's been done. And finally, Formula One cars is all about optimizing engine performance, which means you need to look at radiative transfer. You've got to look at soot and all of that, and interactions with that. These are all transport equations of one kind or the other. Boltzmann equations of one kind or the other. So what is the one that I'm going to be working? So let's move on. So there are many limitations of the Boltzmann equation. You couldn't apply it to liquids. By the way, yet we know we can use Navier-Stokes equations to describe liquids, right? And Navier-Stokes in some ways also limited the Boltzmann, but you can't really apply it. It has to be generalized to account for things like 3-body collisions, 4-body collisions, which makes it really complicated. The main limitation that interests me is the fact that it's only valid and accurate for actually an infinite population size, so that the quantity is predictable. The distribution function is not a random function, all right? So if I take the same system, identical system, I'm going to get the same distribution function. That's important. And so that means that the system is deterministic. That only obtains if the population size is literally practically infinite. Okay? Mathematically, you can show that that's what you would need under those conditions. However, the particle populations, we look at applications that are never really deterministic, right? Because of the fact that we made this discrete particle assumption, and because of the underlying probabilistic, because you're assuming random media, and the fact that these collisions are therefore random fluctuations are always going to be present. And typically we ignore them because this is large enough, right? The system is never infinite. The number of populations is large enough that you can say the fluctuations are small around. But there are applications that exist where random fluctuations in fact dominate. And so the solutions, that at best you can say that system is unpredictable. But we encountered them enough that we need to study them, right? Something as simple as earthquakes, right? Big disasters, major disasters that happen. And so we then have to, and in that case, then knowing just this average phase space density is not enough. Sometimes you can compute a variance and say that's a little bit of extra information you have, but that only makes sense if the system is near equilibrium, which means it's nearly just a Gaussian, right? And so that the mean and the variance is enough. But that's not the case we're talking about here. We're looking at what are called strongly stochastic populations, non-Gaussian random deviations, non-Gaussian random deviations are the norm. They're not small fluctuations of output. So you can formally extend this. So if you know about a little bit about kinetic theory, if you've had some background, you know there's this thing called the BBGKY hierarchy. You go from that account for these higher order collisions, but it's limited. There's almost no practical value if you want to compute, if you want to describe something here. So what we need is this more fundamental probabilistic approach, and there is this theory called branching random Markov processes, stochastic processes. And what I'm going to show you is an application of this to a couple of problems that come up in neutronics, which is neutron transport applications, where there are two types of descriptions, a kind of a coarse-grained description where we look at the gross behavior of the system and we look at the neutron population as just a function of time. And I'll walk you through some of the details there so that you understand a little bit about how these problems are done and what we get out of that. And then there's this fine-grained description where you now have to account for the fact that the particle actually has velocity dependence, it has spatial, it's in a medium that has spatial structure, and so on. Okay, right. So where this arises for especially nuclear engineers is whenever you are in a fissile system, i.e., uranium, plutonium, and so on, where there is only a weak neutron source, is where you will have strongly stochastic neutronic behavior. Where does stochasticity arise? This is fascinating. So you go back. When was the first time when people started talking about stochastic behavior of systems? When did that matter? When was this probabilistic notion formed? One of the earliest one is it was done very thoroughly by Galton and Watson in England. And one of these guys was a reverend. I forget which one. And the other guy solved it correctly. He posed it, one guy posed it, and the other guy solved it correctly. But there's this concern by the British royalty of that they were dying out. And since to preserve royalty, you had to have a male. You had to have a. It's only the lineage goes through the male. And so the question then was, what is the probability that the line will go extinct? And related to a certain rate of production of males versus females. So that became an underlying fundamental process. By the way, when he wrote it, he got it wrong, and he said basically it's probability 1 that it will go extinct. When you do it right, in fact, there is a finite probability that it doesn't go extinct. Line doesn't go extinct. Perhaps very relevant today is infectious disease spread. And we're sort of seeing that. But a lot of that work, if you look at the modeling that's done, is based on Markov processes. You need to know the rate of interaction of people with each other. You need to know migration patterns, right? We all read that now. You've got, so here, this is like a contact network for a particular individual, right? Whether it's family, friends, work, flight, whatever you're taking, and these lines represent the what they call the contagion probability. How likely is it that you will catch? And so if the contagion probability is high, then of course the whole network can be infected, and if it's low, then it can be contained through and so by it being low means that you have to isolate and so on, so quarantine and all of that. So there is a huge industry out there. The only problem with this is when there's a new strain, you need to have data. And you can only get data when there's enough, unfortunately, fatalities and infection rate. People need to come to hospital, and doctors need to know that somebody's been infected. So that takes time. Anyway, but there are models out there, and that work. So a lot of other stuff. Here's the other one: stock market volatility. You've got the daily fluctuations, but on top of that, every now and then there's a crash. 2008 type crash, but even just smaller ones, like when your Dow loses 500 points in one day. Those can be modeled using these rare event, that kind of discrete processes. A lot of statistics in there. And there's this kind of a fun problem I give my grad students when I'm introducing them to this field is that when you're typing, the probability that you introduce a typo as you're typing on a reason, sample size has to be large, is a Markov process. And now you can predict the distribution of typos that you'll create. The more challenging problem is when you don't know the number of typos that are in a book, and you're now reading and you're catching them. That too is Markov, but you don't know how many there are, and so then there is more of an inverse problem there. Anyway, in physics, it all started by very early last century, this investigation of cosmic ray showers. In the nuclear world, with the Manhattan Project, Ulam, statistician, and of course Richard Feynman, they worked on the problem for weapons. They looked at the importance of fluctuations. And then in reactors, Leonard Pahl in Hungary, he developed the first systematic approach, and it was George Ballard Los Alamos that created what's now called the modern theory of neutron transport. So with that, what am I interested in? So this is neutron branching processes, what are those? And I realize I'm going very, very slowly. So I'm going to have to pick up pace over here. And I will not get through my entire talk, I can see that now. So I should finish at 4, is that the idea? Because we saw that, okay. So in any fissile material, you have this thing called fission, where a neutron gets absorbed by a nucleus, a heavy nucleus, uranium, plutonium, and there's an instability there, and there's a it stretches out, breaks up into 2 pieces and 2 what I call precursors, and they have a distribution of masses, and they produce neutrons and radiation, gammas and antineutrinos. There's a whole bunch of stuff that comes out, depending on the energy that's in that fission. But these neutrons can then go on and cause further fissions, right? But in any fission, nuclear engineers are probably used to thinking, if I ask you how many neutrons are produced per fission, you're going to say 2.3 to 3.2, depending on uranium. Well, actually, there's a distribution of neutrons that are produced in any fission. It's a probability distribution, as many as 10. Ignore these are photons, but if you look at this one, the red line is in what's called an induced fission. That's an energetic neutron that strikes a nucleus and it causes fission. So the average that you're familiar with is up over here, just about where it should be, right? But there's actually a distribution. You can have anywhere from 0 up to about 8 neutrons that can be produced in fission. An average overall that is about 2.5, and so on. That's induced fission. The blue line is what we call spontaneous fission. That's that these nuclei, plutonium, uranium, etc., they're radioactive. And there are different paths to decay. One of the paths is just fission. So it's a spontaneous fission. And that produces a slightly softer spectrum, as it were, of fission. But nevertheless, there's a huge statistical variation. Okay? So, why do we use 2.5 neutrons? Why are we happy getting away with that, right? It matters. The probabilities vary, right? There's the highest probability, the most likely is about 4 neutrons or something, right? Okay. So anyway, that is the source of stochasticity. If the effect of these fluctuations cannot be averaged out, then you have. The knowledge of the mean neutron number is sufficient for power reactors. That's where there are enough neutrons, and you've started your reactor up to make sure that you don't end up in a stochastic regime, that these fluctuations are small. But this is not the case in many of the applications. So, for example, when we have a reactor startup with just a weak source, one of the reasons when we start up a reactor, we have a very strong source of neutrons, is to prevent these massive fluctuations from dominating as we approach critical. Okay? And so you want to make sure that you're always. This is a simulation where it starts off very, very subcritical, or very, very stochastic, and then eventually becomes deterministic. Criticality safety. As the famous Japanese accident in Monshu, where they were pouring liquefied fuel, and I guess they were in a hurry and they wanted to empty stuff quickly, and they paid the price. It went to critical from just the source, that spontaneous fission source that was in there. Okay, so and that system is very unpredictable because you're looking at this kind of behavior. Okay. Your reactor is not a burst reactor, is it? Is it a fast burst pulse reactor? No. So you won't see that, but many reactors are designed to study what happens to when you assemble a supercritical mass, and you want to just watch it. And under those conditions, the distribution is very rich. So the common theme here is that you've got neutron multiplication in the presence of weak neutron sources. That's it. So lessons were learned a long time ago that you don't want to have weak neutron sources, but you can, under accident scenarios, you can. It's a big issue in weapons safety, but also you want to study them for research purposes, but also things can happen, right? Accidents. So under these conditions, then talking about the mean number and its variance don't mean anything. Under these conditions, you have to literally talk about what happens to the entire population. Does it become extinct? How does the population grow with time? And that's what you're going to live with. Okay? So in this case, what the kind of parameters that characterize it are the neutron number probability. What is the probability that there would be n neutrons, literally n integer neutrons? What is the probability that that n will be 0? That at some time the neutron population can become extinct. Remember, these are huge fluctuations, so that can't happen. And what's the probability that that number can grow without bound? That's called the divergence probability. Okay? And so and there are other things which I won't talk about, but the distribution of numbers of fissions and the amount of energy that's deposited. All of these are random quantities. And important. So I'm quickly going to, I have a lot here. Clearly I'm not going to get through there. I might just do the first part and be done with it, and just maybe just mention the others. But so we'll talk about, the plan was to talk about what's called this coarse-grained description, what we call a point kinetic model. And then we're going to see how we have to generalize to include phase space. We'll talk about computation of survival divergence, and then I want to give a safeguards application. So these are subcritical applications. These are very, very subcritical applications. Okay. All right, so I have to go through some definitions as soon. So we talk about the system state. That could be just the number of neutrons at any given time. It's a random variable. Okay. It could be more than the neutrons. It could also be the number of precursors that were born. That's random because they're from fission. The total number of fissions is important. Sometimes the amount of energy that's released and deposited in fission is also random. So all of that stuff can be part of the state. A random system is one for which the future state cannot be uniquely determined from a given state. By default, that's a random system. Finally, we talk about, to characterize those systems, we talk about the probability of finding the system in a certain state at a particular instant in time. And it could be conditioned on a particular state before at an earlier time. So we talk about that state changes because of various interactions. And the interactions that matter, they're called mutually exclusive, meaning only one or the other can happen, but not, is that a neutron can disappear. Okay. That happens because it gets captured or it leaks from the system, right? That's disappear. It can, these are using words from epidemics and species, extinction. Neutron can emigrate, that's leakage, right? That can be immigration. Neutrons can come in from a source, that's production due to source. And then there's generation or birth, which is through fission, right? You saw those 8 neutrons that can come out. And finally, there can be a transformation where a species transforms to another one. In our case, there's a precursor that decays and produces a delayed neutron. Okay, so we have to build our model. We need to have what are called transition probabilities. What are the probabilities of an individual neutron, or what are the rate parameters associated with these, right? Which you will see. So, and finally, which I'll say a little bit more in a minute, is the state of the system is assumed to evolve as a Markov process. So, I have to get into the jargon now. And so we have neutron cross sections, right? That characterize the strength of interactions. We have a fission cross section, a capture cross section, and so on. And so if you multiply by that by the neutron speed, then I have units per second. So that gives me a rate parameter. That's the rate at which a particular reaction can take place. So if you multiply this by a small time dt, lambda a is the absorption, then that's the probability of a neutron loss event in a short time dt. S is the source strength, and S dt is the probability of a source event in dt. Okay, so on. And 1 minus that is the probability that in dt nothing happened. That's the null event. If there is a fission, then there is a distribution. Remember, I showed you the distribution, so anywhere between 0 and so Pj is the probability. It's called the multiplicity distribution. The probability that J neutrons are emitted in fission. Likewise, in source, through spontaneous fission, we'll say that there is a different multiplicity distribution. All of these define the basic interactions that when you that combine to give you the change of state. All right. So that we define and then the other argument is that each one of these neutrons is independent of the other neutrons. The path a neutron is going to follow in terms of its chain is going to be independent of what another neutron does, because the neutrons don't interact in the medium. So we refer to this as independence. And then the Markov property that it does not matter how the neutron got to this current state, it only matters what the current state is. And then we can therefore define all these events, loss, fission, source, and the null event, and these are the probabilities. Since this is the probability here, per neutron, there are n neutrons in your state at a given time, and each one of those n are independent. Therefore, the total probability that the state will change is if any one of those n's gets captured, then it goes from n to n minus 1. If there's a fission by any one of those ends and there are new neutrons emitted, then the state changes to n plus nu. Likewise with the particles, and if there's a null event, the state doesn't change. Okay, so this whole picture is based on the idea of a Poisson process, which is a rare event. And so these are very, very small probabilities, and so most of the time nothing is happening. The system is just in its state. And when a reaction is okay. So given these transition probabilities, then we can model the stochastic behavior, what's called the branching process. And we use the Markov process. So I've introduced this quantity called this is the probability that at sometime tk plus 1, there were nk plus 1 neutrons conditioned on the past history. Okay? That probability, if it's a Markov process, will only depend on the current state here. It doesn't depend on all the previous states. So this is equal to that. Okay? So the probability that it's going to change to nk plus 1 at time tk plus only matters, it only depends on what the state was at that last time. So that's the essence of a Markov process. And so then it's known from this theory of Markov processes that such probability satisfies what's called the Chapman-Kolmogorov equation, which basically says that if it's a Markov process, then if there are j neutrons at time s, what is the probability there will be I neutrons at a later time t can be considered as a superposition of all possible paths that the neutron can take to go to that final state. And so that's what it is. It goes from, so in this case it starts at j, it goes to some state k at an intermediate time u, times the probability that it will then go from k to I from between u and t. And then you sum up over all possible intermediate states k. That's the Markov property, right? That's building on the Markov property. And so that leads you to the Chapman-Kolmogorov. All right. So this is, however, not an equation that you can solve. There's no physics here. This is more a statement of consistency, a definition of a Markov process. The Chapman-Kolmogorov equation, written in this form, is just a definition of consistency. You sometimes check if a process is Markovian by showing that it satisfies the Chapman-Kolmogorov equation. To make it practical, we have to make one of these times what's called infinitesimally near the other one. And so what's called last step analysis, u is, when we make it infinitesimally near t, in other words, it's t plus delta t. And what's called first step analysis, it's u is infinitesimally near the initial time. So this is the final time, that's the initial time. So then we get what are called master equations, forward and backward master equations. Okay. So given the time, I'm going to skip a lot of it so I can get you to some results. But you can do what's called first step analysis in probability theory that allows you, that says that the probability to get to a certain event is the sum of all the probabilities through all the different paths it can take, system can take in getting there. So if it's probability of an event E is probability that an event S occurs, times the probability then conditioned on that you'll get E, and then you sum up for all possible events Sk that are mutually independent. So this is known, it's basically the idea of conditional probability and what's called a partition theorem, right? And when you apply this to discrete populations, and I'm going to show you a derivation over here, how to do each of the individual processes, but let me just bypass that, and I can get you to this, what's called the backward master equation. That's the probability that there are n neutrons at time t, given some initial neutrons. In this case, I've got just one neutron at an earlier time. And it's a combination of losses due to, remember what I said, the capture and fission, and then what are the source terms due to fission, and this is the branching process. You see, this is a product of all these probabilities. So it's a branching process, right? You're accounting for all possible contributions. This is known as the differential form of Batman. So now the physics is all in these rates. The rates have come in. Okay, there's your multiplicity distribution. This is for a single initial neutron. To then, if there's a source, you have an auxiliary equation that does the same thing. It looks at the branching effect from all the others. It's better to use what's called a generating function. This is like a Laplace transform, but for discrete variables. We call that the probability generating function. That's defined like that. So n is our independent variable, z is now a parameter, our transform verb, multiply by z to then integrate the probabilities, okay? And so there's some interesting parameters here. If I set z equal to 0 here, all these terms drop out except that one. P0 is the extinction probability. N is 0, okay? So if you know g, you can immediately get the extinction probability. Then if you differentiate this and set z equal to 0 successfully, you can get the individual probabilities. 1, 2, and so on neutrons. We use that approach in safeguards applications. Then if you differentiate these and set z equal to 1 instead, you can get the averages. So you can recover the mean, the variance, in a higher order moment, which we call, these are what are called factorials. So if you apply the generating transform, that very large, n is anywhere from 0 to infinity, right? So this is a very large system of equations. The entire system collapses to this nonlinear equation here for the generating function. Z is our parameter. It doesn't get operated on in any way, but it comes out as an initial condition, and then for the source. The question is, if we can solve this, then we have to invert this in Z, so it's like inverting a Laplace transform, right? And so the first thing we do is we then, as I said, we formulate our problem, and then we try and do some analytical work to get a sense of an understanding of it. And so by looking at some late times and making some asymptotic expansion, we get a pretty good. These are definitions. So for the neutronics people, right, we're also allowing this is the reactivity in the system, and that can be dynamic, time dependent. So when K is a multiplication factor, so if K is greater than 1, you have a supercritical system, and K is less than 1, you're subcritical, and when K is equal to 1, you're a critical system, okay? But on top of this, now we have all these fluctuations. There are some additional parameters that depend on the higher order multiplicities. So there's your mean. Alpha is just the integral of alpha. So if alpha is a constant, that's just alpha t, and that's another parameter that depends on the statistics. So the extinction probability turns out to be exactly that. So there's the mean and there is that, okay? And then the higher probabilities turn out to be given like that, okay? They all sum to 1 by definition. So that's an explicit expression there. Now, so let's look at those. This is a key result. This is what's underappreciated in all this world, okay, that we need to remind. If you do have a supercritical system, what is your expectation of the population? You have a single initial neutron, and you have a supercritical system. What's the population going to be like as it gets very infinitely, as time progresses? Your first reaction is, for the nuclear engineers here, it's going to grow without bound, right? E to the alpha t. As you know, from a supercritical system, point kinetic problem, it's just going to grow without bound. So in other words, deterministically, it says that the population will always explode to infinity if you wait if you let time go to infinity. Well, if you actually look at that result, it's telling you that the extinction probability at time extinction, probability that the population goes to 0, is actually non-zero. Probability that the population will become extinct at time t infinity is not 0. Okay, and moreover, the probability that for finite n, that as t goes to infinity, the probability goes to 0. So, probability of extinction is not 0, there's a value. Probability for any finite value of n is 0, right? Yet, you must have normalization. What this implies is that the rest of the probability mass is at infinity. So that that's population that's exploded to infinity. So the population can only exist. So this was derived for a supercritical system, but you can show it for a subcritical system or a critical system, that for a subcritical or a critical system, the neutron population will always become extinct with probability 1. It's a certainty that if it's a subcritical system, you have 1 neutron in there, it kind of makes sense, it'll all die out, even though they're fluctuating. If it's a critical system, you would think that the neutron population should be flat. So on average, it will be flat, but the fluctuations are so huge that you wait long enough, one fluctuation will set it down to 0. So population becomes extinct with probability 1. For a supercritical system, however, there are 2 possibilities. Either the population will become extinct with that probability there, or it will diverge with the complement. So just a single chain can give you that, right? So those are 2 different things. So you're probably saying, well, I know in a supercritical system, a population can diverge. That intuitively was obvious, but the fact that it naturally becomes extinct is actually very fascinating. And so here's the probability of initiation. That's the divergence probability for uranium and plutonium system as a function of K. And you can see that even if you're all familiar with these experiments, Godiva and Jezebel, and that Solomon says that. Wow, okay. Anyway, so I've been told to back it up. So if you have a source now, then here's the distribution of neutrons as a function of source divided by the average density, okay, for different source strengths. So for now, these are what we call the lower or the weak sources, and then we have the stronger sources. Look what happens. The analytical solution that I couldn't show you looks like this. It's like what's called a gamma distribution. Okay, so Y is the normalized population, eta is a parameter. So there's a normalized distribution. That distribution depends on this parameter eta, which depends on the source and the neutron lifetime. So that's roughly the total number of neutrons ejected over a lifetime. And you'll notice that when something happens, that is when eta goes from less than 1 to greater than 1, the shape of this curve changes. When eta is less than 1, it's going to be monotonic. When eta is less than 1 means that S is small enough. But as soon as S gets large enough so that eta can become greater than 1, it develops this single mode. And then as S gets larger and larger, this distribution gets narrower and narrower and narrower, and you can show mathematically that it tends to a delta function at the mean, which means it's become fully deterministic. Okay? So here what we've understood is that a lot of this depends on the source strength. The stronger the source, the more deterministic you are. Therefore, if you want a predictable system, you've got to have a strong enough source. But if you don't have a strong enough source, if you have a weak source, you're going to get a very stochastic system. Because that was the key takeaway from you. It's quantified a transition point that eta equal to 1 is, we call that a critical point. And you can do more math on this to show various interesting bifurcation phenomena. All right, I think I'm going to have to go get out of here. So here I'm sort of adding neutron energy and direction, which is velocity dependence. And so I will, let's see over here. So that was for very gross systems. What is the population in the system as a point model? In reality, you have a device, right? A reactor or some sample, and then you have, there's a spatial dependence and energy dependence of the neutron. So this is now the divergence probability for a neutron injected at different points in this. There it is. There's a problem. It's a 7 centimeter uranium-235 ball with 5 centimeters of graphite shell. Okay, that's unfortunately the spectrum. I'm going to have to not talk about the methods I use. We use an eigenfunction method as well as a nonlinear iteration method. And so this is the divergence probability with a neutron injected at different points. So you can see out as you go towards the exterior of the reactor of your assembly, the probability of divergence is low because the neutron can leak out. But if it's at the center of the assembly, then the probability is much higher. That makes sense. But this is a very different picture from just a single number that we looked at before. But it's still the physics is still the same. That there is a non-zero extinction probability. Okay? This is. Let's see, for different cases. This is. So this is, we're looking at convergence with different modes. This was an eigenfunction expansion, so these are a number of modes. The first mode is simply the critical shape in the whole reactor. And that already, but one more mode is sufficient to capture the bulk of the behavior. And so that simplifies the problem tremendously. You use a K spectrum, you just know classical criticality spectrum, expand your solution in those modes, or actually modes of the adjoint system, and you will get 2 modes is enough. Which means that you can now reduce your problem to like a point kinetic problem, right? You project out the information, and that verifies. So this is huge. I'll skip that. 5 minutes, please. Let me just say something here. So nuclear security applications. So what are we concerned about in nuclear security or nuclear safeguards, right? Nuclear terrorism. Is material being taken away, taken out clandestinely anywhere in the fuel cycle, from enrichment through manufacturing, through burning in the reactor, through reprocessing. There's a lot of opportunities to take stuff out, and so in order to prevent that, you have to. How are you going to address that problem? You have to basically monitor everywhere, and how are you going to monitor these things, right? And so there's something called passive detection, where what we do is and this is not just for our fuel cycle. Okay, it's not just here. It's not just fuel cycle. It says special nuclear material in transit, right? Somebody bringing a truck over across the border. And so in this case, then how do we detect that? So this is passive detection. What we do is we rely on this fact that the background signal is very strongly what's called Poisson. It has a very, very different shape from the signal from neutrons coming out of fission. And so if you can detect the neutron distribution, you will find a very unique signature. And that signature will at least tell you that you've got some multiplying material, you've got some. And even if you, so the challenge then is, of course, it's very easy to shield a small amount of material, right? You've got to grant the bad actors that much intelligence, so they put stuff around it. But then the challenge is in the detection. And you need to have sufficiently sensitive detectors, but modeling and simulation can really play a major role. So here what we've got, for example, is this is the same distribution here. So we've got it's terrible, I don't know what happened there. But we've got 3 different spheres. These are actually spheres of plutonium. It's actually, you all know about Jezebel. Jezebel is the other reactor experiment at Los Alamos. It's literally just a sphere of plutonium. It's got 80% 239 and 20% 240. This is a contaminant, and it turns out that 240 has a very strong spontaneous fission source. It's huge. It's massive, and so unless somebody has access to very, very pure plutonium 239, there's going to be a significant signal from just the 240. So that's very telling immediately. If you see 240, you've got 239. And 230, uranium has a much weaker source, so there you have to be particularly sensitive. But in any case, so here's a 335 gram sphere of plutonium, and this is the probability of seeing 0, 10, 20, 30, 40 neutrons. Right? And this is the spontaneous fission distribution. This is a single fission distribution does that. Then those neutrons, before they get out, are able to cause more fissions, and the more mass there is, the more fissions you're going to cause, and more neutrons you're going to produce. But then the statistical signal is something like this. This is very, very unique to the systems. And if you look at the background, first of all, if you see a background neutron signal, you've got trouble. So usually there isn't much of a background signal in neutron. There's background other stuff, but neutrons are not like not like charged particles or X-rays. There's always radiation from decaying from background materials, even concrete, right? Bananas. So there's always background, but but the background is very, very high, but it's very, very narrow. So if your detectors are sensitive enough to detect multiplicity distributions out in this range, and there's a lot more complicated stuff that goes into developing something like this, then you've got that, and so that's what's called passive detection. We didn't have to do anything; we just observed the system. All right, I use this backward approach to define equations for the probability distribution. These are now transport equations. You're all familiar with them. They're set up what are called adjoint transport equations. Probability that there are n neutrons, that if you have one neutron injected at r with an energy E in some direction omega at some initial time s, this is the probability that you will observe n neutrons that you saw there at time t. Very complicated, this is a transport equation, but nuclear engineers love solving these. We've got this down. We know how to solve equations like this, right? Multi-group data, we have to get data, we've got very cross-sections. Now you have scattering in there, you've got fission spectrums there, you've got the fission cross-section, mean number, and so on. So this is, if I want to observe 40 neutrons, I got to solve 40 of these couplements. So Jo Saxby over in Imperial College actually did that for her thesis, and this is her result. I'm not going to get into the challenges, but we modeled this, what's called the famous Los Alamos experiment, the Los Alamos plutonium sphere of plutonium surrounded by different amounts of polyethylene shells. And that's what you try and conceal the signal, right, by having something like that. So we were able to model it. I'm not going to get into it, I just want to show you a representative result. This is the extinction probability of a neutron in that. So this is as a function of time. This is position in the sphere. So this is towards the outside. So the probability is you can see, is very high. It goes extinct because the neutron leaves. So there are no neutrons in there. Probability if it is low in the center, if the neutron is injected towards the center, because it can't go extinct because it now can create more neutrons and the like. But there are some very interesting features as you see. It depends on this is the direction. This is a neutron pointing outwards towards the sphere. This is a neutron pointing inwards. This is a fast neutron, right, as opposed to thermal neutron. Thermal neutrons have a higher cross-section, and you start seeing these very interesting features that track boundaries and things like that. So what we're pointing over here was that there are spectral features that have not been considered in those measurements and simpler models that are done. There's more. I think it's the same idea. It's basically, here's a probability of observing 10 neutrons with a fast and a thermal neutron pointing in different directions, injected at different points in the sphere. And you can see that the probability shape is very, very different. Okay, so it all depends on where your source is, what kind of shielding you have around it, and it's going to tell you what sort of signals that you're going to see. Okay? And these are the probability scales. These are small probabilities, but detectors are extremely efficient. I think Dr. Saw will agree, hopefully agree with me if he's here. But that's it. Okay, let me just finish then. And so we've looked at what are called strongly stochastic systems. These are subcritical and supercritical. So the last application was very subcritical. It was just a sample. First application was very supercritical. And we've shown that with weak sources, right? Even though that 240 source is very strong, it's still weak in the context of that plot I showed you where it doesn't transition. We've shown that the population actually deviates significantly from that predicted by just the low order moments, mean and the variance. These things that are called survival and divergence probabilities are the key parameters to characterize such strongly stochastic systems. The moments don't do it anymore. Right? You can't fit to Gaussians. And the multiplicity distributions for safeguards are very efficiently computed using this Blackman-Master equation approach. So that's what we're doing in New Mexico. Work has been largely funded by Los Alamos, and recently we were partnered with the University of Michigan in just last year when they won this consortium for what's called monitoring technology and verification. It's an NNSA program. If you know what an NNSA university programs, NNSA have put all their money in one basket, and that's to fund a consortium. And they fund it for 5 years. If you win one, you're in good shape. If you lose, tough. You're out of it for 5 more years. It's unfortunate. But we partner with Michigan, and so in this area, this MTV, we're looking at developing these methods for that. So I apologize for running over, and thank you very much. And if there's time for questions, I'm happy to go ahead. Yeah, absolutely. So yeah, when I put up an equation like this, right here. So those are this is the total cross section. That's the scattering cross section. That's the scattering that a neutron with some energy E comes out with E prime. So all of that fission cross section spectrum. That data is important. Well, no, these are known extremely good. So if we want to use what are called multi-group methods, which is what we're doing, yes, we do everything. But we use anywhere near from 6 groups. All of these were done with 6 groups. Now, if you're interested in the actual spectrum of the neutrons that are coming out, which is where we're going next with it, to look at actual external detectors, then resolution of the energy will be important, yes.
So the detectors that are actually in use are simply detecting the number of neutrons, not
no, energy as well. So in fact, energy resolution is important, but you don't need ultra-fine energies. If you're looking for resonances and everything, and if you've got what I call pulse heights, then you're in trouble. But that's not what we're looking at here. We're looking at usually by the time the neutrons come out, they've had a few collisions, the spectrum is actually, and so in fact, this calculation computed the spectrum as well. It was all there. We just showed it. It's just hard to show.
But when you get the result of a certain number of certain number
right.
of certain energy.
Right.
What energy?
So that'll be broken up into remember energy is an independent variable, so you have to discretize it.
Are you looking at
we're looking over the so fission energies are, for example, a couple of MeV. So you start at 2 to 3 MeV down to thermal, and then beyond that, yes. So what we have to do is learn a lot more about experiments. So we have our colleague at Los Alamos now who remember all this experiment, this Godiva experiment, Jezebel, Top Hat, all of these are critical assemblies, supercritical assemblies they have, and they have measured a lot of data. And so we've got a bunch of new methods we have to develop first, and the hope then is what they're undergoing, then we'll compare against experiments. But the data is there. And there's a lot more fascinating stuff that's coming out of this, and that's why a probabilistic approach is necessary. There's something called correlations. Neutrons are different from, when you have a very subcritical system, the correlations are very strong, energy and angle correlations. They have never before been computed, but in a description like this you can. And so that's where we are headed. Prinja.
I might have talked to this earlier, but then this exact same equation, if you have looking at reliability of systems with constant
Absolutely. Markov Process change rise.
and then you have history dependent, you end up with a semi-Markov process. But actually, if you will take a little bit more complicated history dependence of failure, reliability, nonlinear integrity French equations.
But you don't need to even look at history dependence. This backward approach gives you a nonlinear set of equations, even with just Markov process.
No,
But
the cross sections.
yeah, right, exactly. So,
All right, so thank you, Dr. Prinja, for your
Thank you.
presentation.
thank you again. What?
Over there. And I invite you all again to join us at the reception upstairs in 100. Let's thank our speaker one more time.
Thank you very much. I was expecting this. Thank you. Thank you again.
It might look like a lobby. Oh, that might be like a nice spot. Yeah, that's a good idea. Maybe get a picture of him with the flag, and then like just with it.